Welcome back to the deep dive. So if you've ever found yourself, staring down a routing table entry or troubleshooting some connection that just won't work,
Oh, yeah.
that moment of panic when you realize you need to figure out subnet boundaries and you needed to do it like 5 minutes ago?
That moment is, I think, universal in networking.
Right.
Whether you're setting something up or, trying to figure out why something's broken, knowing the actual edges of your network segment is it's non-negotiable.
Absolutely.
These calculations, finding the ID, the broadcast, the usable range, are probably the most practical, repeatable skills in the whole TCP/IP world.
So that's our mission for this deep dive. We're going to look at the source material to basically shortcut your path to getting this right every time.
Mm-hmm.
We need to take an IP address and its mask, and from just that, pull out 3 critical pieces of information.
The 3 must-haves. First up, the subnet ID. That's the official name for the segment.
The identifier.
Exactly. Second, the subnet broadcast address. That's the very highest number in the range.
Okay.
And finally, the really important part for day-to-day work, the range of usable IPs.
Yeah.
The ones you can actually give to a computer or a server.
We're going to use a core example from our sources to kind of anchor this whole thing, especially for the first part.
A good one to stick with.
Yeah, it's IP address 172.16.150.41, and it's paired with the mask 205.255.192.0.
Which is a 18 for anyone who prefers the slash notation.
Right, 18. So let's unpack this whole structure.
To really get the calculation, we first have to get what a subnet is. An IP subnet is, well, it's just a set of numbers.
Just a block of numbers.
Block of consecutive numbers. It's a fixed, finite block.
And the size of that block, how many addresses are in it, that's all down to the mask, isn't it?
Completely. It's about the number of host bits, which we call H.
Right.
So if you have H host bits, the total number of addresses in your block is 2 to the power of H.
Right.
And this is a huge but. 2 of those are always reserved. You can't assign them to anything.
The boundaries, the edges are untouchable. So let's start with the bottom, the low end.
The first number, the absolute lowest one in the whole block, is reserved. That's your subnet ID. It's like the network's own address.
It's what shows up in routing tables.
Exactly. It's the address that says, hey, if you want to talk to this segment, aim for this identifier. People sometimes call it the resident subnet or just the prefix.
I can already see where people get confused because they throw around network ID and subnet ID like they're the same thing.
And they're really not. That's a super important distinction we have to make.
Okay.
In the old classful world, the network ID, for our example, 172.16.16.17.01 would just be 172.16.0, the whole Class B network.
But we're subnetting it.
Right. We're using that 18 mask to chop that huge network into smaller, usable pieces. The subnet ID is what identifies those smaller blocks, and that's the number we're trying to find.
That makes perfect sense. So the subnet ID is the low watermark. What about the high watermark, the top end?
That would be the subnet broadcast address, the highest number in the block.
Mm-hmm.
And what it does is actually pretty cool.
Go on.
It's a destination address. If you send one packet to it, every single active host on that subnet gets a copy at the same time.
Oh, so if my router sends a packet to the broadcast address, every PC, every server on that specific subnet gets it.
Yep.
That's why the sources call it the directed broadcast address.
It directs the broadcast only to the hosts inside that boundary.
Okay, so you have the floor and the ceiling. What about the good stuff in the middle, the usable range?
That's everything else. And honestly, it's the easiest part to find once you know the boundaries.
How so?
The first usable address is just the subnet ID +1. And the last usable address is the broadcast address -1. No crazy math there.
Just simple addition and subtraction. But first, yeah, we have to find those boundaries. Okay, so the sources give us 2 ways to do this. There's the deep and slow binary
That's
method.
the foundational one.
And then there's the quick, practical decimal shortcut. We have to start with binary, even if it feels slow, because it's what proves why the shortcut works in the first place.
Absolutely. If you get the binary logic, you get subnetting, period.
It all comes down to the bits.
The whole logic is built on this one fact. Every address in a single subnet has to share the exact same network prefix part. The host part is what changes.
Let's apply that to our example then. 172.16.150.41 with an 18 mask.
Okay, so 18, that means we have 18 prefix bits and 14 host bits.
Yeah.
32 minus 18.
Got it.
And those first 18 prefix bits, they have to be identical for the ID, the broadcast, and our IP address.
Okay, so first step is converting the address to binary. The first two octets, 172.16, are fully covered by the mask, right? That's 16 bits right there.
Yep, so we can just copy and we don't have to worry about them at all.
The action is all in the third octet.
The third octet, which is a 1 of 50, and binary 150 is, let's see, 100, 101, and 0. Now, since we need 18 prefix bits in total, we need to borrow the first 2 bits from that third octet. Those are prefix bits. The remaining 6 are host bits.
So the binary for that third octet is split. It's 10 for the prefix and then 010110 for the host part.
Exactly. Now, to find the subnet ID, the lowest possible number, we have to set all 14 of those host bits to 0.
The 6 in the third octet and all 8 in the fourth one.
Correct. We keep the prefix part, the 172.16, and we keep the 10 from the third octet. Everything else becomes a 0.
So the third octet's binary becomes 100,00.
And here's the rule that trips up so many people. When you convert back to decimal for the IP address, you have to do it 8 bits at a time.
Always.
I see. So 100,000,000 in a binary is 128 in decimal. And the last octet is all 0, so it's just 0.
Wow, okay, so the binary logic proves it. The subnet ID is 172.16.128.0.
Yep. The IP we started with, ending in .150, actually lives in the .128 subnet.
That's a great way to put it. Okay, now for the broadcast address.
Same logic, opposite rule. The broadcast is the highest number, so we take those same 18 prefix bits.
And set all 14 host bits to 1s this time.
Exactly. So we keep the 172.12, we keep the 10 prefix in the third octet, but now the other 6 bits are all 1s.
So the third octet is 101111111.
Convert that 8-bit string back to decimal and you get 1091. And the fourth octet, all 1s, is obviously 255.
So there are our boundaries. The subnet ID is 172.16.128.0, and the broadcast is 172.16.191.255. It's slow, but doing the binary gives you this, absolute confidence in the answer.
It really does. And just as a quick aside, a computer does this way faster. It uses Boolean logic.
A bitwise AND, right?
A simple AND operation between the IP and the mask gives you the subnet ID. It's way more efficient for a CPU. But for us humans, we need a better speed trick.
That is the key, because on an exam or when you're live troubleshooting, you do not have time to be writing out 32 bits.
Not a chance.
And the source material really emphasizes that if you master this decimal shortcut, you can get these answers in under 15 seconds.
And the whole method is just about exploiting how predictable these subnet blocks are.
Let's start with the really easy cases. If you have a standard Class A, B, or C mask, a 255.0.0 or something like that.
Then there's no real math. It's simple. If a mask octet is 255, you just copy the IP address number for that octet, for both the ID and the broadcast.
And the mask octet is 0.
You write 0 for the subnet ID and 255 for the broadcast. Done.
Easy. The brain power comes in when we hit what the sources call a difficult mask.
Any octet where the mask isn't 0 and it isn't 255.
We call that the interesting octet.
And that's the one single place where you have to do any calculation. For our main example with the mask 255.255.192.0, the interesting octet is that third one.
The 192.
That's where we use the most important tool for this, the magic number.
I have to say I love this term magic number because it really does feel like it just unlocks the whole puzzle. So how do we find it?
Step 1. Calculate the magic number. It's just 256 minus the mask value in that interesting octet.
Okay, let's switch to a new, cleaner example from the sources to show this off, then we can come back to our 18. Let's use IP address 130.4.102.1 with mask 255.255.24.0.
Okay, good one. So the interesting octet here is the third one with the value 240.
Right.
The magic number is 256 minus 240, which is 16.
16. And what does that number actually represent?
Conceptually, that 16 is the block size. It's the jump between each subnet ID. The subnet IDs for this network have to be multiples of 16.
Okay, that's the aha moment right there. The magic number gives you the pattern. So step 2, finding a subnet ID with it.
You look at the IP address value on that interesting octet. In this case, it's 102. And you have to find the multiple of the magic number 16 that is closest to 102, but, and this is key without going over.
Okay, so let's list the multiples of 16. We have 0, 16, 32, 48, 64, 80, 96, 112.
Whoa, stop. 112 is too high.
Right, our IP is 102, so 112 is over. The correct multiple must be 96.
So that's our number. Since the first 2 octets of the mask were 255, we just copy 130.4. The fourth octet mask was 0, so we're 0. The subnet ID is 130.4.96.0.
Wow. That is incredibly fast.
It is.
Okay, now for the last piece, the broadcast address.
Even easier. You take the subnet ID value in the interesting octet, which was 96, you add the magic number, and then you subtract 1. The formula is just ID plus magic minus 1.
So using our example, 96 plus 16 is a 112, minus 1 is 111.
That 111 is your third octet for the broadcast address. And since the last octet of the mask was a 0, it becomes 255.
The broadcast address is 130.4.111.255, and that means the usable range for that whole 20 subnet runs from 130.4.96.1 all the way through 130.4.111.254.
Now, just to prove it works, let's apply this magic number method back to our first example, the 172.16.150.4112.
All right, idea, let's test it. Our interesting octet was the third one, mask value 192. So what's the magic number?
286 minus 192 is 64. So all the subnet IDs in this network jump by 64.
Our IP value in that octet is 150, so we need the multiple of 64 that's closest to 150 without going over.
Multiples are 0, 64, 128, 192.
192 is too high, so it has to be 128.
And there it is. The decimal method instantly confirms what binary told us. The subnet ID is 172.16.128.0.
And for the broadcast address, ID plus magic minus 1, that's 128 plus 64 minus 1, which is 191.
Giving us a broadcast of 172.16.191.255. It works perfectly.
The magic number makes it almost instantaneous. The sources really deliver on that speed boost claim.
You know, the power of the decimal method for speed is just undeniable.
Yeah.
But it's so important to remember that the binary method is what gives you that foundational why.
You really do need both in your toolkit.
Yeah.
So to recap our main example, 172.16.150.4118, which we've now picked apart with two different methods.
The subnet ID is 172.16.158.0.
And the broadcast address is 172.16.191.255.
Right.
Which means if you're actually configuring a machine on this network, your pool of available addresses runs from 172.16.161.191.254.
It's a huge range. And it's all unlocked by mastering that one little calculation in the interesting octet. And that actually leads to a final thought for you to explore. The source material has this little reference table in it. It lists the 8 difficult mask values.
128, 192, 224, and so on.
Right, all 8 of them. And next to each one, it lists its corresponding magic number. So 128 gives you 128, 192 gives you 64, 224 gives you 32, 240 gives you 16. You get the idea.
Okay.
So my question is, why might memorizing those 8 pairs save you even more precious time than calculating 256 minus the mask every time?
Ah, you're removing that first step of the math completely.
Exactly. When you're under pressure, trying to fix a critical outage, reducing your cognitive load is just as important as knowing the theory. If you see a 224 mask, you don't calculate. You instantly know the jump is 32.
You skip the subtraction and go straight to finding the multiple.
It's the ultimate evolution of the shortcut.
A perfect demonstration of how deep technical understanding can always lead to a faster, more effective way of doing things. That was a deep dive into decoding subnet boundaries.